Hello and welcome back to another Orange Coast College mathematics video. In this video, we're going to take everything that we've learned so far about polar graphs and we're going to try and sketch them. Now, number one wants us to sketch a graph of r equals 1 minus sine of theta, and then it wants us to use symmetries to try and simplify the graphing process. Right, a lot of times the reason we want to use symmetry is because there's a million points that we could graph, but why would we want to do all of those when we see that this graph is actually symmetric? So we only have to do a portion of all those graphing points, and then we can just kind of reflect them wherever we can. And that reduces the amount of work that we actually have to do. So, first off, let's look at what kind of a function this is. We have r equals 1 minus sine of theta, and let me rewrite this to make it hopefully a little bit more obvious. We have r is equal to 1 minus 1 times sine theta. Now from here, I see that there's a coefficient here, there's a coefficient here. So this looks like a limacon, right? What's the equation for a limacon? We have r is equal to a plus or minus b times sine theta. In this case, we have minus. So this really is a limacon. Now, what do we see? First off, we know that it's sine, so it's going to be on the vertical axis. So, is it pointing up or is it pointing down? Well, this minus sign right here says that it's actually pointing down. So it's a limacon that's pointing downwards. Now we can figure out one more thing about it, right? We can look at the ratio of the coefficients a and b. So our coefficients are 1 and 1. So if we look at a divided by b, it's going to be equal to 1 divided by 1, which is equal to 1. So this ends up being the special case that this is actually a cardioid, or a heart. So it's a cardioid that's pointing downward. That's what we should expect. So now let's try to figure out some symmetries. So let's start off with our polar axis symmetry. Now to test for my polar axis symmetry, I need to replace theta with negative theta. So let me write that down. Replace theta with negative theta. And if nothing changes, we get our original equation back, then it has polar axis symmetry. So let's go ahead and rewrite our equation just down here to make it a little bit easier to see. Our original equation was r is equal to 1 minus sine of theta. Now I want to show that f of negative theta is equal to f of theta. So f of negative theta is going to be equal to 1 minus sine of negative theta. Now we have an identity that says sine of negative theta is actually equal to negative sine of theta. So we can continue in red. So this is going to be equal to 1 minus negative sine of positive theta. But now we have two negative signs right here. So a double negative will turn this into a positive. So this is actually equal to 1 plus sine theta. However, this is not equal to f of theta, right? F of theta is 1 minus sine of theta. So we do not have polar axis symmetry. Now let's check for pole symmetry. Now for symmetry about the pole, we need to replace theta with pi plus theta. So replace theta with pi plus theta. So we want to show that f of pi plus theta is actually equal to f of theta. So let's go ahead and plug it in. So f of pi plus theta is going to be equal to 1 minus sine of pi plus theta. Now I'm going to use the identity sine of a plus b is equal to sine of a times cosine of b plus cosine of a times sine of b. So this then becomes 1 minus sine of pi times cosine theta plus cosine of pi times sine of theta. Now I put it in brackets because this negative sign is going to have to distribute to both of these pieces. Now let's see if we can simplify anything out. So this sine of pi, what is that equal to? Well, sine of pi is equal to 0. So that's actually going to cancel out this entire left term. Now what is cosine of pi? Well, cosine of pi is -1. So we end up getting 1 minus -1 times sine of theta. This double negative becomes a positive, and so we're left with 1 plus sine of theta. But 1 plus sine of theta is not equal to 1 minus sine of theta. So f of pi plus theta is not equal to f of theta. It's not equal to our original. So we do not have symmetry about the pole. Moving on to our last one, we have our vertical axis symmetry. Now for this one, we need to replace theta with pi minus theta. So replace theta with pi minus theta. So f of pi minus theta is going to be equal to 1 minus sine of pi minus theta. I'm going to use the identity of sine of A minus B is equal to sine of A cosine B minus cosine A sine B. So this then becomes 1 minus, and then in brackets we have sine of pi cosine of theta minus cosine pi times sine theta. Well, sine of pi is going to be equal to 0, so it's going to cancel out this whole left term. And cosine of pi is equal to -1. So we have 1 minus sine of theta. 3 negative signs is the same thing as 1, so this is going to be 1 minus sine of theta. Well, that is our original equation. This is f of theta. So we finally have a match. F of pi minus theta is equal to f of theta. We have symmetry about the vertical axis. And if you go back to the picture of what a cardioid looks like, especially when it's pointing down, it makes sense that it should have symmetry over the vertical axis. So now let's actually try to figure out some points. So when trying to graph these points, we need an angle first. So let's go ahead and look at what our angles should be. Now we know that we have symmetry over the vertical axis. So all I have to do is get 1/2 of this. So I only need these angles. If I can figure out the points from these angles, I can take those and flip it to the other side, and I should be good. Now, because typically we go in a counterclockwise motion, I'm going to go ahead and start with the angle 0, go up to pi halves, and then I'm going to start over here with 3 pi over 2, and then make my way back to 0. Once I do that, I will have covered all of the angles, kind of like in the counterclockwise order. And then, once I have those, I can reflect them over the vertical axis. So, let's write some of these angles in first. So, we have the angle 0, and then pi over 6, and then pi over 4, then pi thirds, and then finally pi halves. So then I've reached the top part of the circle, and I'm going to skip that whole entire left side, and I'm going to go all the way down to the bottom, which is 3 pi halves, and I'm going to make my way up back to 0. So now we're going to go to 5 pi over 3, and then 7 pi over 4, 11 pi over 6, and then back to 2 pi. But 2 pi is going to be the same as 0, so I'm not going to have to actually redo that one. So now that we have all of our angles written down, let's actually find the function values. So in this case, our theta is going to be equal to 0. So we have 1 minus sine of 0. Well, sine of 0 is 0, so this is equal to 1 minus 0. And so we get 1. So our point is going to be 1, 0. Now let's do it with pi 6. So we have 1 minus sine of pi 6 and pi sixth is going to be equal to 1/2. So we have 1 minus 1/2. That's going to be equal to 1/2. So our next point is going to be 1/2 at an angle of pi over 6. Then we have 1 minus sine of pi over 4. Now sine of pi over 4 is the square root of 2 over 2. So we get 1 minus the square root of 2 over 2. Now if you have a calculator and you're actually allowed to use it, this is no problem. Plug it into a calculator and you'll get an exact value. But if you don't have a calculator, the square root of 2 is about 1.4. So this is almost equal to 1 minus 1.4 divided by 2. Now what's 1.4 divided by 2? It's going to be 0.7. So this is going to be 1 minus 0.7, and so we get 0.3. So our point is going to be 0.3 at an angle of pi over 4. Now we have 1 minus sine of pi thirds. That's going to be equal to 1 minus the square root of 3 over 2. Now again, if you have the calculator, just get the exact value. But if you don't, it's a good trick to remember that the square root of 3 is almost 1.7. It's actually a little bit bigger, but 1.7 is good enough. So this is approximately equal to 1 minus 1.7 divided by 2. Now, what's 1.7 divided by 2? 0.85. So this is going to be equal to 1 minus 0.85, which is equal to 0.15. So we get the point 0.15 at an angle of pi thirds. Now we've reached the top of the circle, so let's look at pi halves. So we have 1 minus sine of pi halves. Now sine achieves its maximum value at pi halves, so this is going to be 1 minus 1, which is going to be equal to 0. So our point is 0 at an angle of pi halves. Going to the bottom of the circle, we have 1 minus sine of 3 pi over 2. Sine actually attains its smallest value of -1 here, so we have 1 minus -1. The double negative makes it a positive, so we have 1 plus 1. It's going to be equal to 2. So we have 2 at an angle of 3 pi over 2. Now 1 minus sine of 5 pi over 3. We're going to have 1 minus negative square root 3 over 2. Now we've already solved what the square root of 3 over 2 is. It's about 0.85. So this is going to be 1 plus 0.85, right? The plus comes from the double negative. So we get about 1.85. So our point is 1.85 at an angle of 5 pi over 3. 1 minus sine of 7 pi over 4 is going to be equal to 1 minus negative square root 2 over 2. We already solved for that earlier. We know that square root 2 over 2 is approximately 0.7. So this is going to be about 1 plus 0.7, and so we get 1.7. So our point is 1.7 at an angle of 7 pi over 4. And oops, these should be approximately equal, not actually equal. Let me fix that. Now 1 minus sine of 11 pi over 6 is going to be equal to 1 minus -1/2. And this is going to be equal to 1.5. So we get a point of 1.5 at an angle of 11 pi over 6. We've come all this way, so we might as well just do this. We know that this should connect back to where it originally started, but let's do it anyways. So 1 minus sine of 2 pi is going to be equal to 1 minus 0, which is going to be equal to 1. And so we end with 1 at an angle of 2 pi. our starting point. So let's go ahead and graph all of these points in red. At an angle of 0, I had a value of 1. So we'll go out to this first circle and plot our point along the 0 angle. We then had a value of 1/2 at pi over 6. So we'll follow that pi over 6 angle and we'll do 1/2. We then had 0.3 at pi over 4. So it's a little bit smaller than that. And then we had 0.15 at pi thirds. So that's even smaller. And then we had a value of 0 at an angle of pi halves. So those were these angles. And then we followed this all the way down, and we come back to these angles. So we then had a value of 2 at 3 pi over 2. So follow the 3 pi over 2 and go to the second circle. Then we had a value of 1.85 at 5 pi thirds. So it'll be somewhere over there. We then had a value of 1.7 at 7 pi over 4. And then a value of 1.5 at 11 pi over 6. We then finish it off by coming back to where we started, right here, at a value of 1 at an angle of 2 pi. Now an angle of 2 pi just means we've gone around the entire circle once, so it's the same angle as 0. If we connect all of these, we're going to get the first part of our cardioid. Now if I really wanted to, I could figure out all of the points over on the left side, but we have that symmetry available, right? We can flip this over the vertical axis. So let's go ahead and figure those out really quick. Now, when dealing with this type of symmetry, we had to replace theta with pi minus theta. And so we're going to do the same thing here. We're going to keep our r values the same. The only difference is that instead of theta, we're going to have pi minus theta instead. So, for this first one, we have a 0.10. My r value is not going to change, so we're still going to have 1, but my angle is now going to be pi minus 0. So, pi. We then have 1/2 as our value of r. Again, doesn't change. In fact, I'm just going to write all of the r values right now since they don't change. The only thing that's changing is our angle. So we have pi minus pi over 6. So that's going to be 5 pi over 6. And then we have pi minus pi fourths. So we're going to have 3 pi over 4. And then we have pi minus pi thirds. So we're going to have 2 pi over 3. Then pi minus pi halves is going to be pi halves. Then we're going to have pi minus 3 pi over 2. So that's going to be negative pi over 2. And then pi minus 5 pi over 3 is going to be negative 2 pi thirds. Pi minus 7 pi over 4 is going to be negative 3 pi over 4. Pi minus 11 pi over 6 is going to be negative 5 pi over 6. And finally, pi minus 2 pi is going to be negative pi. So now that we have these points, we can actually put them on the graph. So, at an angle of pi, we had the value 1. So, it's out here. Then at 5 pi 6, we had an angle of 1/2. So that's going to be about right there. At 3 pi fourths, we had a value of 0.3. So that's going to be about there. And then we had a value of 0.15 at 2 pi thirds. So that's going to be somewhere right there. And then at pi halves, we had a value of 0. So I'll put that on top. Now, with our remaining angles, we need to be a little careful. When we move in the counterclockwise direction, that's considered to have a positive angle. But we can move in the opposite direction, in the clockwise direction. That is considered having a negative angle. Since all of our remaining angles are dealing with negatives, we're going to be moving in this direction. So when we have an angle of negative pi halves, we're doing 90 degrees, but in the clockwise direction. So starting from 0, 90 degrees over, we're actually going to be at 3 pi over 2, or negative pi halves. Now that had a value of 2, so it landed right on top of that red dot. Now we have a value of 1.85 at negative 2 pi thirds. So 2 pi thirds in the clockwise direction will land us on 4 pi thirds. So it'll be about right there. Then we have a value of 1.7 at negative 3 pi over 4. So around there. Then we have a value of 1.5 at negative 5 pi over 6. And then we end up at a value of 1 at the angle of negative pi. So the point we've already plotted. So if we connect these, we'll get the second half of our cardioid. While my graph isn't perfect, this does have symmetry. It has that symmetry over the vertical axis, right? The red and the blue match each other. So this is our final sketch of our graph. And now we can move on. Actually, before we move on, let's take a closer look at our cardioid real quick. Our function was r is equal to 1 minus sine theta. And we said that a was equal to 1 and b was also equal to 1. What did we see here? The point here had a value of 1, which is the value of a, right? Now the point right here also had a value of 1, so that was also a. This point right here was a value of 1 minus 1, so the absolute value of b minus a. And this point down here had a value of 2, which was our a plus b. 1 plus 1 is equal to 2. So those points still matched up. Okay, that's going to do it for this part, and I hope to see you in the next one, where we deal with our last problem.